We have looked at the fundamental theorem of calculus that gives us a way to evaluate the definite integral of a continuous function on a closed interval without actually having to do the limiting definition for that definite integral. In this video, we're going to talk about another implication of the fundamental theorem of calculus. Some people talk about this being the first part, other ones the second part, but another thing that comes out of a fundamental theorem of calculus is looking at a function that's defined as an integral. So here the definite integral as a function of x is the focus of this video. So if f is a continuous function on a closed interval, then the function capital F of x, so we have our case sensitivity between the naming of the functions, defined by this capital F of x being defined by the integral from a constant, the start of your interval, to x, a value that varies in that closed interval, of small case f of t dt. So that's being our definition of our new function, that function is actually continuous also on the closed interval from a to b, and it's differentiable on the open interval between a and b. And furthermore, it's true that if you take the derivative of this function that's defined as an integral from a to x of f of t dt, you actually get this function in x. So what we're going to do here in looking at this is the first thing we're going to do is just look at some examples where we have our capital F of x function defined for a specific function, evaluated at some values, but then we're going to look at what this other part says, that the derivative of our capital F of x function is actually going to be our integrand function of x. So let's get started with that. So here our function, capital F of x for this example, is defined to be the integral from 0 to x of cosine t dt, where x is a value that I pick somewhere between 0 and pi. So notice my lower limit of integration here is the start of the interval for which the x's can be picked. Now, we could go through and generally find what we have for our capital F of x by doing this work of the integration on this right-hand side. Or we could, for each of these, take out the x and put in what they're asking us to find and evaluate it that way. But you'll get the same thing. So what I'm going to do just to prove that point is I'm going to evaluate the first one by taking out the x in the definition of my capital F of x function and then getting that value out, and then after that seeing how we could get our general equation for that function and then go from there. So here my capital F of pi over 4. Well, think about any other time that you are asked to evaluate a function at an input value. And you've been doing that for a long time, right? You go and you find your variable, your independent variable of your function, take out that variable and replace it with the expression or number that you're supposed to evaluate it at. And that's all we want to do here. It's just that it's a little bit uncomfortable for us at first because here my variable of my function is actually an endpoint of the integral. It's not the variable that is in the integrand itself. So when I look at finding capital F of pi over 4, well, this is capital F of x, and x is there. So this is going to be the integral from 0 to pi over 4 of my cosine of t dt. So then this, remember, now that I have my definite integral from a number to a number of a function, that's going to be a number. I can use my fundamental theorem of calculus from helping me evaluate a definite integral here and that will give me my value out. So my capital F of pi over 4, we're going to get by finding an antiderivative of cosine t. An antiderivative of cosine t is sine t. Evaluate that from 0 to pi over 4. And then remember, you evaluate it by putting in the upper limit of integration to the variable minus the lower limit of integration to the variable. So my f of pi over 4 is sine of pi over 4 minus the sine of 0. And the sine of pi over 4 is the square root of 2 over 2. The sine of 0 is 0. So I get for this that that's the square root of 2 over 2. So that way of evaluating my function would require me to do this process of finding my antiderivative, plugging in the numbers, and then evaluating it out. It would be like if I were working with an equation of a line and I had several different x inputs and I want to find the y outputs, but I don't have it solved for y. So every single time I would have to resolve it for y. That would take a lot of time. It would give me the right answers, but a better thing to do would have been to solve the algebraic equation for y in the first place and then just plug in the varied x's that we want to use. So here, instead of plugging it in and integrating it new each time, what we could do is take and look at this capital F of x and then think about how we would integrate this using the work with the Fundamental Theorem of Calculus. So we are going to find an antiderivative of cosine t. An antiderivative of cosine t is sine t. But I'm going to evaluate that from 0 to x. So then we take out the variable and replace it with the upper limit of integration. So take out the t and put in the x. I have sine x minus the sine of 0, putting in the lower limit of integration. And my capital F of x for this particular function is sine x minus, well, the sine of 0 is 0. So I just get that this capital F of x function is just the sine of x. So since I did all that work once now, I can go ahead and say, well, that means for f of pi over 3, I'm just going to go and evaluate the sine of pi over 3. So my capital F of pi over 3 is equal to, well, the sine of pi over 3 is the square root of 3 over 2. And then my capital F of pi over 2 is equal to the sine of pi over 2. And the sine of pi over 2 is 1. So working through what this definition of my capital F of x is equal to and getting its equation actually aided in being able to evaluate it at different input values easier. What if you know that you have a continuous function on a closed interval and your function capital F of x is defined to be the integral from a to x of f of t dt, and you weren't wanting to evaluate it at values, you actually wanted to find the derivative of it? Well, that's what we're going to do next. So let's look at what if they ask us to find the derivative of our function that is defined in this manner. So first of all, I have my capital F of x is defined to be the integral from 0 to x of cosine t dt, and in the direction it says find f prime of x. So when I think about asking me to find f prime of x, they want me to find the derivative with respect to x of this integral from 0 to x of cosine t dt. Now, when I'm looking at how this is defined, I have to make sure that I have my lower limit of integration be and my variable be at the upper limit of integration. Now, what I'm going to do with this is work from the inside out. So my capital F of x is equal to the derivative with respect to x of, well, the integral from 0 to x of cosine t dt. Remember, we're going to find an antiderivative. An antiderivative of cosine t is sine t. Evaluate that from 0 to x. So then I have is the derivative with respect to x of, put in the upper limit of integration minus put in the lower limit of integration. So this is sine x minus the sine of 0. But the sine of 0 is 0. So this is just the derivative with respect to x of sine of x. The derivative with respect to x of sine of x is cosine x. So my capital F prime of x is equal to cosine x, which is what I had in the integrand of the original integral defined function, but now it's in the variable x because of what happened in our application of working with the definite integral and plugging in the upper limit of integration, which was the variable x, minus the lower limit of integration, which was a constant. So this is going to happen every time. You're differentiating an integral, and derivatives and integrals are inverse operations of each other. So when I differentiate an integral, I'm back to the original function that I had. And once I realize that that's true, I can say that's what they were trying to tell me here. That when my function is defined as that type of an integral, and I take the derivative of it, I am going to get the function that was in the integrand in that variable x now, instead of in the variable t. So that's huge, because now if I'm asked again to find a derivative of this function that's defined as the integral from 0 to x of a continuous function over that interval, which this is, then I don't have to go through all of those other motions, all of this other stuff to see that I just get that back. I can just jump to the case and say, this is just going to be this function, the square root of, but now it'll have the x's in its place, the square root of x squared plus 1. A much better way of going about this than if I tried to actually do this every time, especially if I don't have at my disposal or remember or figure out how to find an antiderivative for that function, when I'm just going to differentiate it back and get the original function anyway. So that's really what this helps me with. Now, this last example that I have actually is going to use that, because the example that I have, it's going to need a little bit more. It's still asking me to find the derivative of that capital F of x function defined as an integral from a constant to, but it's to an expression in my variables whose derivative is other than 1. And remember, when you're differentiating a function who is a composite function and it's acting on an expression whose derivative is other than 1, then you had to use the chain rule when you differentiated. So not only do you have to take the derivative of the outside action, keep the inside stuff alone, but then you also have to multiply by the derivative of the inside expression. So when I actually go and do this capital F prime of x derivative, it's true that it's going to end up being this sine of that input variable. so I have the sine of x cubed. But it's also going to get multiplied by the derivative of x cubed. That's the input expression. So the derivative of x cubed is 3x squared. So my f prime of x, capital F prime of x for this one is 3x squared times the sine of x to the third. And that gives you several different examples of not only evaluating function types that are defined this way, but also using that application of the second fundamental theorem of calculus to find the derivative of functions that are defined in that way. Well, thank you for watching my video, and please push the like button if you found this video to be helpful, and also look for other videos that are in my calculus playlist, or I also have playlists for statistics, trigonometry, algebra, etc.